Lasse is a postdoctoral fellow at the University of Toronto, funded by the Carlsberg Internationalization Postdoctoral Fellowship. He works with Professor Alana Spirou on machine learning for quantum computing, developing near-term quantum algorithms, and some hardware proposals. Prior to joining University of Toronto, he obtained his PhD from Aarhus University, where he was working on designing proposals for small quantum systems with quantum computing applications. And today he'll be talking about his recent work on information flow in parameterized quantum circuit. So Lasse, please take it away.
Thank you, Abhinav. So can you see my slide?
Yeah.
Everything okay? Okay, great. Well, thank you for the kind introduction. So today I would like to tell you a bit about some work I did together with my collaborators, Abhinav, Bill, and Felix, on information flow in parameterized quantum circuits. But before we get into sort of the meat of the talk, I'd like to start with a little bit of the motivation. So as you're probably all aware, there's quite a lot of buzz around this idea of using quantum computers to solve problems that are hard to solve using a classical computer. Sort of a challenge when trying to solve problems with quantum computer is that in order to do so, you sort of have to navigate this huge, exponentially large Hilbert space in order to make your way to the solution you're searching for. And sort of for some problems, that's no problem. You can write down a prescription for sort of steps you need to take, and you can sit down and you can write out these circuit diagrams without any problems. But for quite a broad class of problems, you can't do that. You sort of don't have a good idea of what circuits you should put, which gates should go where. And so it becomes very challenging to find the solution to your problem. Now, one way to sort of mitigate this problem of algorithm design is to take your quantum circuit and add some tunable parameters to it. Because then, even if you didn't manage to come up with the perfect circuit in the first try, you can sort of take these parameters and you can tune them and change them and optimize until you get a circuit that gives you the solution you're searching for. Right, so these variational algorithms, these parameterized quantum circuits are super popular right now in the NISQ era. But of course, they do come with some challenges, some drawbacks. So one problem is that the optimization landscape, when you're trying to optimize the theta parameter, tends to be a bit problematic. It can have these large barren plateaus where the gradients vanish, and it can in some instances have a lot of poor local minima. And actually, even if you manage to solve these serious problems, even if you manage to use clever tricks to avoid them, optimizing is actually still a lot of work. And the reason is that you would usually want to have gradients to do gradient-based optimization of this parameter, and that scales linearly for quantum circuits. So if you have n parameters that you want to update in a given step of your optimization, you need to do 2n evaluations of expectation values. And one expectation value might require thousands of measurements. So if n is large, each step ends up taking a lot of time and effort to do. So really, it would be great if we could keep n low. Or maybe if we could, at each step of the optimization, pick only a clever subset of the parameters to update. Because then, if we could do that in a way so that we still make good progress, but optimize on fewer parameters, then we can sort of keep this n low and avoid having to use too much effort in this optimization. So that's sort of the motivation here. Can you pick clever subsets of the parameters to update at each step? Now, before we get into the whole optimization part of the talk, I would like to sort of start by simplifying these circuit diagrams a bit, because we're not going to be interested in the exact gates. We're just going to be interested in the structure of how information flows through them. So what we might like to do is map them to a graph that shows that better. So what we want is we want a node for each qubit state at each point in time, and we want edges indicating the directions that information could flow. So in this particular example, we have 4 qubits that start in 4 states. So we should probably map that to having 4 nodes at the beginning here. And then if we sort of pass through the circuit towards the right, we first arrive at some single qubit gates. So we update the state of each qubit with these gates, so we should probably have 4 new state nodes. And each state only depends on the state of the same qubit at the previous step. So these single qubit gates should probably have an information flow that looks something like this, going from the initial to the new state. Right. And then, okay, we arrive at the 2 qubit gate, and that updates the state of the 2 top qubits, and it updates it in such a way that information can actually flow between the top and the qubit number 1. So it should probably look something like this. Now we have the possibility of information flow sort of diagonally as well. So those are sort of the basic rules. Those are how you sort of can progress through the circuit and map every gate to a structure and arrive at this kind of graph representation where each edge sort of indicates all the possible paths that information can flow through. Okay, so with this kind of simplified representation in mind, let's start thinking about optimization strategy. So how can you pick these parameters so that, how can you pick these parameters in a clever way? Which parameters do you want to update at each step in the optimization? So one strategy would be to just update every parameter in your circuit at every step of optimization. That's sort of what I've tried to draw here. All the edges are active at every step in your optimization. Another approach that's been proposed is to sort of go through the circuit in these vertical slices. So first, you start by fixing most of the parameters of the circuit and only updating the parameters of the first slice of the circuit here. And then you do that for a while, and when you're happy with those parameters, you fix them and you move on to the second slice, and you update the parameters of that slice. And then when you're happy with those, you fix them, move on to the third slice and the fourth slice, and then maybe you iterate through all of the slices multiple times. Now, that's a cool strategy, but what we thought was really the information flow in these circuits, right, is from left towards right. So things are flowing from the initial states towards the final states over here that we measure. So flows of information is horizontal. Maybe it would make sense to think about horizontal structures as well when picking these parameters. So to be concrete, assume, for instance, that we are interested in optimizing with respect to some measurement on this qubit here. Okay, how could information flow to that particular state? Well, certainly not from these gray regions. You can sit down and you can sort of convince yourself that if information flows from left to right, it cannot make it to here from here. So we only need to care really about this causal cone or this light cone in black here. Okay, and then, right, we could, for instance, pick a path here. So this is a possible direction that information could flow and influence the state we're measuring at the end. So that might be an idea, right? Pick these information flow paths and optimize only the parameters that are touched at each path. Now, probably not all paths will be created equal, right? Sometimes we might have have problems where maybe this bottom part of the circuit doesn't end up influencing the output we're interested in very much. And in that case, picking paths that spend a lot of time down at the bottom would be sort of a waste of time, because we would be spending a lot of effort optimizing parameters that don't end up mattering things we're interested in. So maybe it would be nice if we could figure out a way of picking paths that we know will be contributing a lot to the information flow, and a way to sort of avoid those that don't contribute to the things we're measuring. So that sort of motivates trying to come up with a metric to quantify information flow. And a lot of this stuff I'll be presenting now is very much inspired by the work of Catherine Hyatt et al. Here, but with a few twists and adjustments to fit our needs. All right, so the first thing to notice is that so far I've only been talking about circuits with single and two qubit gates. So the only places where you have branching, where you have the ability to take one path or another, is in the two qubit gates. So let's focus on figuring out a metric for those. Right, so we have a two qubit gate, or equivalently our graph representation over here. Now we can write up our two qubit gate in some basis as here. Right, so it's just that gives us 16 complex numbers that describes our gate. Now we can then take those 16 numbers and use them to construct a 4-qubit state here. So for instance, the C0 gate, we could sit down and we could write out as a state representation of that gate, like so. Now the intuition to have here is that the A and B qubits here correspond to the input states, and the C and D qubits correspond to the output states. So for instance, down here, we would have the input 0, 0 to the C0 would give us the output 0, 0. And the input 1, 0 gives the output 1, 1. That's sort of how you can understand the construction of these states. And it also gives us a sort of one-to-one correspondence with these graph objects, right? Because the two input qubits here now correspond to two input nodes. Here, this is the input state of the first qubit, and so is this in some sense. The advantage of mapping from a 4x4 matrix to the state is that now, if we imagine there's a lot of information flow along here from A to C, then surely that must mean that the input and the output here, that these two nodes become very correlated. So really what we do by translating to these states is that we turn information flow into correlations of these 4 qubits. So a lot of information flow between A and C should correspond to a lot of correlation between A and C in this state, more or less. So to quantify information flow, all we need to do is quantify these correlations. And there are ways to do that. So using something called mutual information. So the basic idea with mutual information is that, well, you start by tracing out the things you're not interested in. So if we're interested in the information flow between A and C, you start by tracing out everything but what's in this red oval here. And you actually sometimes trace all the way to the individual nodes here. And then you quantify the von Neumann entropy of the resulting state-machine matrix. And the reason why that's interesting, and an interesting property, is that it sort of quantifies the amount of correlation you traced away when you did those traces. So specifically, if A and C are very correlated, then when doing the trace to go from having the full system to having the individual nodes, we'll trace a lot of correlation away. So it should lead to a large increase in this von Neumann entropy. So simply by tracking the changes in entropy, you can actually quantify these correlations. So basically, you can go from information flow to correlation, then from correlation to these entropies, and then arrive at this neutral information to quantify your information flow, sort of loosely speaking. Right? And this will be large if there's a lot of correlation, a lot of information flow, and we want a metric where the distance is short when there's a lot of information flow. So you can sort of wrap it in a minus log to create that effect. So that's the construction of the metric for the two horizontal parts, AC and the BD distance. Now, it's sort of an interesting question now is, can we then, how do we do for the diagonal? Can we use just the same formula for those? And that would be nice, but it turns out that there's some problems if you try to do that. So specifically, it doesn't seem to work very well for controlled gates. So let's, for instance, assume we're considering a C0. Right, then if we wanted to use this formula here, what we should do is we should trace out degrees of freedom to sort of zoom into the AD, for instance, to evaluate the diagonal distance here. But if you think about the C0 gate, it doesn't actually change the state of the top qubit here, right? At least not in the computational phase. So really, we would expect A and C nodes here, the input and the output of the top qubit, to be maximally correlated, because this state is always the same as that state. So really, when we do this trace, we've already traced out the maximal amount of correlation. So we've generated the maximal amount of entropy. If you actually do the calculation, you get the maximal mixed state from a control gate like this. So when you start doing further traces, you can't actually generate any more entropy. It's already maximum. So your changes in entropy will be zero. These mutual informations will be zero. And so what this metric is trying to tell you is that no control gate can allow any information transfer between qubits. And that's sort of a problem, because that's not the kind of behavior we want. So we need an alternative, and one way of reasoning, what we thought about was this mutual information instead. So what the reasoning is basically that if there's a lot of information transfer between the top and bottom qubit, then surely what happens at the top part here and what happens at the bottom part here should correlate somewhat. So there should be some mutual information between the top nodes and the bottom nodes. And that's exactly what we measure with this mutual information. So that's an idea. Wrap it in a minus log and propose that as the diagonal metric. Right, so we have this idea. We should probably check whether it gives reasonable results before we start applying it to anything. So let's check it on a few simple gates. The identity, what happened, and the swap. So for the identity, what you can sit down and calculate is that the diagonal part here, those distances become infinite. So what it's telling you is that there's no information flow diagonally, only horizontal. So information just flows straight onto an identity gate. And for the swap, similarly, you get that the information flow straight doesn't happen. That distance is infinite, and instead information only flows in this cross pattern here. So that seems to make sense to me, right? An identity doesn't do anything, and a swap swaps the information around. That seems pretty reasonable. What about controlled gates then? Well, looking at a controlled Y rotation, you get distances that look something like this. So when the angle is close to zero, you get that the diagonal distances, in blue here, diverge, become infinite, and you get the identity again. You get just the straight transfer of information by this finite horizontal distance. Whereas if you start increasing the angle, the diagonal distances goes down, indicating more and more information transfer between the qubits. until out here you reach the maximally intact node. So that also seems a reasonable behavior to us. So it seems like it works fairly well for simple gates, and furthermore, you could sit down, you can check that it's actually invariant with respect to single qubit bases. The fact that I've been using the computational basis states for some of my arguments isn't actually super important, right? It's invariant with respect to what basis we're using. Okay, so now we have an idea for how to pick parameters when optimizing, and we have a metric that might help us pick good paths when we're doing the optimization. So let's see if it actually works, this kind of approach. So let's try it out on a benchmark. Specifically, let's consider a 2D lattice with a Heisenberg XXZ model. So we have a 2D lattice, and nearest neighbors have this form of interaction here. And let's try to see if we can find the ground state of this system using 2 layers of this hardware efficient answer that I've been drawing for at least the first part of the talk. And let's try out whether we can do this with a few different optimizers. So first of all, let's try out the global strategy, where we optimize every parameter, every step. And then let's compare that to 2 path-based approaches. One using just a random path, and one using the shortest path. So the path that this information metric claims is the one contributing the most to information flow. So just to be a bit more specific, the way these path-based approaches will work is that they will start by looking at the first term of the Hamiltonian. And then they'll say, okay, this involves I and j qubits. Then it will construct the causal cones of those 2 qubits, and then it will pick a path that causal cone, either the shortest or a random path, depending on which strategy we're thinking of, and then do one parameter update on the parameters of that path. Okay, and then move on to the next term. Construct causal cones, update a path's parameters 1 step, and then the next term in the Hamiltonian, and then the next, and so on, so forth. So iterating through the Hamiltonian term like that. Right, so how does this all work out? Well, I brought 2 plots here. The paper contains some more, but what we sort of in general see is that so we have the energy of the y-axis here and the number of iterations of the x-axis. So really what you want is the lines to go down to the ground state as quickly as possible. And what we see is that the random path and the shortest path in red and black here seems to converge faster than the global strategy, the stochastic gradient descent. And so that's good news. And furthermore, it seems like using the shortest path might help a little bit, at least in some instances, this problem. So that's also sort of nice. Seems at least on the surface a bit promising for this metric-based approach. Now, a fun thing about having a metric is that you can actually draw it out. So you can get an idea about, okay, what does this metric think is important, and therefore, what does your optimizer think is important? So what I have here is a circuit that was optimized for the Heisenberg model, and then I picked an output node here, and then I've colored all of the nodes so that they are more colored the closer they are in metric distance to this output node. All right, so this sort of indicates where would the optimizer focus. And what you sort of see is that it seems to be a bit sort of locally focused, right? The qubits close to the output seems to get more attention than those further away. That sort of, it indicates that there's some locality imposed by using this metric. Now for the Heisenberg model, that's probably not too bad. There might be some local structure to the ground state. And furthermore, because you're constantly iterating through different Hamiltonian terms, this output will actually change as you go through the optimization. So sometimes it will be down here, sometimes it will be up here. So even if you're looking at the problem locally, you actually get to visit the whole circuit. So it makes sense that the metric would like this kind of problem. But an interesting question might be, okay, what if you don't have the things? What if you don't have local structure or don't have this kind of iteration through the whole system? So to sort of test that out, let's consider a different benchmark. Let's consider the problem of looking at a bit string and determining whether it contains an even or an odd number of ones. And let's force the circuit to take that information in and encode the answer, whether it's an odd or an even number, into the state of just a single output qubit, specifically the first one. So here we have a problem where you need to look at the whole input bit string, sort of a global problem in that sense, and you're only visiting one output qubit in the optimization. Yeah.
A couple of minutes before
Okay, yeah. So I will hurry and say that in this case, the shortest path seems to struggle, right? The random path still does well, and the global optimization does okay, but the shortest path struggles a bit. And that's probably because it never gets information from the bottom qubit here, because it keeps focusing locally on the top qubit. And actually, you can sort of try to test this hypothesis by forcing it to sample a path from every of the inputs. And in that case, you see that actually when you're forcing it to take in the whole global input state into account, you sort of restore the parity between the random path and the shortest path, indicating that that was probably the problem. Right. So to quickly sum up, so we've proposed using path-based optimization to pick good subsets of parameters to optimize at each step. And we've proposed a metric to quantify information flow to allow you to pick specific good paths to try and optimize, or at least hopefully pick good paths. And what we've seen is that random path-based optimization seems to work very well, and that the metric-assisted path-based optimization seemed to work well in problems with local structure, but seem to be struggling in problems without a lot of local structure. And of course, that might be down to using a pretty simple strategy when using the path or the metric to pick paths. Right, you could imagine sampling in a more complicated way, maybe sometimes picking the longest path, or in some other way using the metric in a more complicated setup than just picking the shortest path at each point. So I think that might be worth further investigation in the future. But with that said, I think I will finish the talk by thanking my collaborators and my supervisor, Alan.
Okay, thanks, Lasse. Thank you for the wonderful talk. So I think we have time for one question at least. So if anyone has any question, feel free to unmute yourself. Okay, it seems there's no question. I feel like the talk was very clear. So at this point, I think we can probably stop the recording, and this can act as the end of today's session. But if the two speakers or if you have any more questions, the two speakers will stay on call for a couple of minutes, and we can chat with them for a while. So let's thank both our speakers.